one last push, and then we're done with turbulence. Yeah. So we have about an hour. Um, we have to understand what is large eddy simulation. That's the only goal. Um, it's you know, this is very interesting topic overall, how large eddy simulation works. But I want to start with providing context after this. Yeah. So our goal is to look at these two legs of this very important topic. So LES function is able to do the things it does because we are able to make progress in each one of these. Now, what I want to focus next 2-3 slides is to say what has changed between when we started doing LES modeling and what is now. And then we will just dive into the details of what is large eddy simulation. Okay, so there is a, before we start anything, and we'll look at this more tomorrow also, we have to know what are the challenges and what problems this method solves. Okay. Now, the most critical thing I feel is the ability to predict emissions, unburned hydrocarbons, NOx, and to some level soot. Also, although soot depends a lot more on chemistry, so it's a lot less understood that way. But that's the main advantage of LES. There are so many examples. Like if you go to industry, you ask any of them, they'll give you so many examples of how before they had LES, their ability to predict what they call smoke number, which is how they characterize how much emissions they have, was so much more difficult than after they had LES, and things were just magically better, right? So for those kinds of predictions where small-scale physics dominate what happens, LES is very good, and this is where we should use it. Now, there are other problems where it's not very good and introduces other kinds of issues. So LES is overall still expensive. It's not something that you can do on a laptop. It still requires a supercomputer. We wouldn't call this supercomputer nowadays. We'll call it a cluster, right? In a cluster, if you go to most companies, they will have clusters of the size of 5 or 6 petaflops. To give you context, Meta has a cluster that's more than 10 exaflops, or at least 10 exaflops. So aircraft companies are not Meta. Their revenue is not the same as Meta, right? So they have clusters, but they are vastly simpler. So, which means that when you do LES, to them, LES is like doing DNS. Like what Meta would call DNS on their whole machine is what GE would call LES on their machine. They're still using all the resources available to them. Okay, so which means that typically you can do few calculations using LES, but not hundreds of them. Okay. So in the real world, challenges are very different. So first of all, when you do this calculation, any partial differential equation, you need boundary conditions to solve those equations. And if you're an aircraft engine, you're not going to simulate the whole aircraft engine, like the compressors and the turbines. You're really simulating a part of it, which is the combustor. And when you're simulating the combustor, you need the inflow from the compressor fed to this combustor. And how can you know what that unsteady flow is going to be, right? So you need to model it somehow. And when you model it, and because partial differential equations, especially those that are elliptic hyperbolic, just like what we have for Navier-Stokes, they're vastly dependent on the boundary conditions. So if you make errors in boundary conditions, the results you get will also be erroneous. So the whole calculation is not useful. So uncertainty in the boundary conditions is very important. So you have these errors at the boundary. Your ability to understand what happens because of the errors is limited because you can do only so many calculations a day. If at all, you can do one calculation a day. Okay. The other problem is time. We talked about this before. If you had very long time events happening in these combustors, it's very difficult to simulate them. You can do steady state operations that are over 10 or 50 residence times of the combustor. But if you want to go to like seconds or minutes of operation, that's still not feasible. That's very difficult to do. So you have these two limitations, right? So all of what we're talking about modeling is within these limitations. Now, let's say emissions are no longer of interest to aviation, okay? It seems like this some days, right? So if emissions don't matter, the purpose of LES is vastly diminished. Okay? It has very limited use if certain things don't become critical. So that's very important. The tools we deploy really depend on where the economic advantage is. If it's not there, there's no point in using these tools. Okay? So you have to learn within this context, what are these limitations? Now, there are mathematical abstractions of this, which we'll look at tomorrow. But for now, this is something to remember. And I just got a reminder that I have no power on my computer. Okay. Oh, this is not. Hey, can you help me with the power supply? Oh, there's one here. Okay. I just woke him up. All right, let's see if this works. Okay, perfect. Okay, so we have to know within this context. So there are a few things that have changed, and this has become more commonplace in industry, so it's good to know also. So since the 80s up to, say, early 2000s, our motto for modeling is predictive accuracy at any cost. It doesn't matter what the computational cost is. If you are able to have a model that can accurately represent the true physics, you would go for it. Now, this doesn't make sense if you think through this, right? If cost does not matter, why not just do DNS, right? But that's unreachable. So essentially, if you can use all of the supercomputing power available to you, and you want to use as complex a model as possible to get as close to the physics. So if you look at all model development in that time frame, they were all like this. Each model, each year, there'll be a new paper with 4 more terms, new coefficients, different kind of representation. So it'll just become more and more complex. And it was becoming obvious by early 2000s, there's no solution to this. We will keep making the models more and more complex, but we will never solve this problem of matching quantitatively what we need. So we had a switch in thinking, and we went towards what is called quantifiable accuracy. So we want to do simulations, but we need to guarantee that our simulations will be accurate within some error margin. And that's a very different philosophy altogether. This brought in notions of uncertainty quantification, Bayesian analysis, things of that nature, which engineers would never care about before. Yeah. So this was very different. So that lasted for a long time until machine learning put a stop to all of this. Yeah. So we want to look only at these two, and we'll go through this process. So the way it works is that you have some complex physics. You have a governing equation, not the one I wrote, but the correct ones, right? You take them, and then you have to come up with what is called a reduced fidelity framework. So this is just mathematical derivation, and you will come up with a set of equations that are easier to solve. And when you derive those equations, you need to have made assumptions that you can show these equations are easier to solve. So you cannot just take the same equations, rewrite them in a different form, and claim, oh, now it's easy, right? So you should have made some abstraction that limits their scope. So that's what we want to look at first. That's the LES framework. Invariably, when you do this reduction, you will find that there's information that's different between the full system and this reduced system. And that difference, you have to somehow model it. This is what is called modeling, combustion modeling or anything else. So that's called models. In this case, it's called unresolved terms. We'll see what this means in a second. And once you put in models, you can no longer trust this implicitly. Like the Navier-Stokes equations, we trust. We don't question whether they're right or wrong. We just say we solve it, we get everything, right? Technically, they're not right, okay? So if you go through the derivations for a reacting flow, there are a lot of assumptions made. Many of them will not match up if you go into the details, but we forget all of them, and we say Navier-Stokes equations is the truth. Yeah? But once you knowingly put models into them, you cannot be so sure anymore. And so you need to have what is called validation, where you have to go to experimentalists and you have to convince them that they should do something that you can use, and then they sometimes oblige, and then you try to use that for validation. Yeah? Together, this process gives you a prediction tool. And with that prediction tool, you go and do whatever simulations you want. Okay? So you need a validated LES model to be able to do this. And so what people would do is build more and more models because they would build a model. The experimentalist will provide some experiment. You'll try to simulate it, and it will not work out. It'll be night and day. So what are you going to do? You cannot just say the experiments are wrong. You have to come up with something else. So you come up with a different model. And then you try it again, and it won't work, and the process continues. So instead, what changed was building models with quantifiable accuracy. So what you do is you take the governing equations, same as before. You also know that there are uncertainties in boundary conditions. You feed that into the equation. You take that into considerations. You do the same reduced fidelity model, but you see that block has changed now. You have models for unresolved terms, but you also say how much error are you incurring by using that model, which is a very difficult question to answer. So to come up with that estimate of how wrong your model is very difficult. But if you're able to do that, now I can tell that if I use LES with this model, my predictions will be off by this much percentage. My estimation, not that that's the truth, my estimation of it. You again have to do validation. Now the validation data has to be a lot different because you now have this model uncertainty included. And with that, you get what is called a probabilistic prediction tool because you have used a probabilistic approach here or things like this. So in this case, you don't do a single LES calculation. You will do a suite of LES calculations, and the result will be some average of those or some statistics based on the results you get. So this is what changed. And so when we go through the process, we have to keep this in mind. We have to get to this aspect, the uncertainty in model prediction. Okay? So with that, this is large area simulation. Now, I would never teach this at 4:30 at the end of a 7-hour day. Okay, this is not for a. Even when you're fresh and you're doing this, it still is very confusing. So I'm not. I don't expect the math to stick. Okay. But what I want you to understand are only two things: why LES works for these kinds of flows, and what is different about it from everything else before, or whatever other modeling that we did, okay? So those are qualitative arguments, right, so that you can remember. The math of it, you can figure out yourself or not figure out, it's okay, it doesn't matter. So very simple way to think about it. Spectrum, there's no way to get around it. So this is the Kolmogov's theory-based spectrum. Y-axis is the log of energy, x-axis is the log of length scales, but 1 over length scales, right? We decided things that be complex. So this 1 over length scales. So which means the leftmost part of the x-axis are the largest length scales, and the rightmost part are the smallest length scales. Because 1 over a small number is large, so it moves to the right. Okay? Now, what is important to remember is the y-axis is in log scale. So if you look at the peak of that value, it's about 10 power 4 or something like this. So that's some units, that's some energy. If I look at the lowest energy that's there in the smallest scales, that's about 10 power minus 3. 7 orders of magnitude difference in energy. So LES makes this very simple observation that the small scales have less energy, so we don't need to worry about it. This is the only argument. So you don't need to simulate all the scales. You simulate only a set of scales that you care about, and the rest of it you model it away, especially when they are at the small scales. So it artificially introduces this cutoff, and you cut off the spectrum at that, and you say, whatever happens below this, I'm going to absorb all of that into a model, and that's my turbulence model. Now, combustion, and we just saw right now, happens at the small scales. So especially if your reaction thickness is very tiny, like very small, comparable to eta or things like that, they all happen at the small scales. So which means this philosophy will not work for turbulent combustion. Okay? So now we are at an important point. we want to use LES. It's worked great for turbulence. People have been doing wall-bounded flows and pipe flows in the 1980s. Everyone is super excited. And then you try to use it for combustion, and you run into the first day, first slide, you have a problem. Combustion happens at the small scales. LES says, get rid of the small scales, right? So we have to reconcile that notion. So this is what we have to understand. Yeah. So that's it. And of course, there's a way around it. Otherwise, we won't have this whole lecture, right? So there's a way around it. Yeah. And that way around it is the manifold-based method. So we'll look at it all in the morning, okay? So not today. Because that is an interesting way to do modeling. So it's interesting, so we'll look at it tomorrow. Today, we only have to know why we need modeling at all and how does it look in the equations and so on, okay? So I'll skip this one. This is not critical for what we're doing. So LES has a number of steps. And I've written this using, I tell all my students, you should never make slides that have so many words and no pictures. So here's a slide with all words and no pictures, right? And lots of words. I do this specifically because you have to understand there are many steps that we write down, okay? We can write down, we can write equations, and then we take those equations, we go to a computer, and we discard all of that. And we will solve our own version of the equations, and we'll get what we get. So that is something also we have to understand. So LES is all paradoxes all around. You say something, you do something else. You cut off the small scales and you say, this is the most important for combustion, right? So all of this paradoxes. So it starts with two principal ideas. You have to use what is called a filtering operation. So signal, if you do signal processing, you know this. You take a signal that has a lot of frequencies. You remove the highest frequencies. You filter it out, right? Bandpass filters. So that's what you want to do. You take a signal, turbulent flow field, and you filter it, and you come up with something that's a little smoother, and that's the flow field that you want to solve. Now, to solve equations, I cannot just keep filtering the field because I don't have the DNS to begin with, so what can I filter, right? So instead, I filter the equations themselves, okay? So I take the governing equations, DNS equations, I filter the equations without solving anything, by the way. I filter the equations, and I come up with the filtered governing equations. And these equations, by the very fact that I've filtered them, will not contain these small eddies that are problematic. They will only contain scales up to some cutoff filter width. And so now I'm good. I can solve it using a much coarser mesh than what I would have needed for DNS. So everything is good, right? So this is the important part. Now, the moment you filter something, filtering is a process of eliminating information, and you might have missed some critical information. For instance, you saw how that filter was placed in the inertial subrange, the vertical line. So in the inertial subrange, there is no removal of energy because dissipation happens at the smaller scales. So if I cut off all the small scales, how is dissipation going to happen? So I need to feed dissipation into the problem. So that's a model. So I need to model how dissipation happens, things like that. And then I have to solve these equations. I won't go into this. That by itself is a whole topic. But we need to solve these equations on a grid, which introduces its own problems. Integrals and convolution are very good for evening lectures. So I'll go with this. It's not very important to know all of these details, but some of the symbols matter. So my filtering process, like if you know signal processing, is a convolution process. You take a signal over some distance or some time, you apply a weighting kernel to each point, you sum it up, and you get a smoother signal. So that's what so you remove all the high frequency components. So if you write it in space, that looks like this. You take a box, let's say, that's easy to visualize. You take a box, there's a lot of turbulent flow inside. I take all the points inside, I measure at every point what the velocity is. I average all of that, and I say that box now has only one velocity, u, okay? And I call it u filter. So instead of all these structures inside that box now has only one velocity, okay? That box has to be relatively small. I'm not talking about the whole domain, but a small part of the domain. And I can think of the size of that box, that sides of the box, to be the cutoff filter width. So if I set some box size, I can say everything within the box is now uniform. I take only one value from it. So that's the filtering operation here. Okay? There are properties, mathematical properties, again, not super critical, but we need to have this. More words. So the filter width is now an important quantity because you arbitrarily placed a cutoff and said that this is where I'm going to stop solving anything at all. Right? So there's a cutoff here. So that filter width now becomes part of the problem. This is now a parameter. If I do two simulations at two different filter widths, they are actually truly different simulations. Right? If I choose a cutoff filter width, I'm saying everything below that I'm going to model. Every scale below that I'm going to model. So if I change the location of that filter, I can now control how much I model and how much I actually truly simulate. So I can change the ratio of resolved physics to unresolved physics, the small scale physics. So this is where the term resolved fields comes from. These are the physics I choose to solve using partial differential equations. And then there's another part, those are the small scales that I choose to model. Now, of course, if my filter width goes all the way to eta, I recover DNS, right? Because now nothing needs to be filtered. So everything is being captured. So there's no point in doing any modeling at all. Okay? So this filter width can take you all the way to DNS if you keep making it smaller and smaller. Now, typically the suggestion, the recommendation is that the filter width should be in the cutoff, should be in the inertial range. This is not what I was expecting. So the whole thing is jumbled. I'll change it, but not on the fly. So the details of this is not critical, but what we saw in the last slide was a convolution integral in which there was a weighting kernel, G. And there are many ways to model this weighting kernel, and so you can use like Gaussians or sharp spectral and things like that. So this is the same technology that you use for any signal processing. You should get roughly the same things here also. Now, if you do this, you'll get this, and this is the part that's interesting to see. So you see that, let's start with the right plot. The left plot is a little bit more tricky. If you look at the right plot, there are the thin squiggly lines, which is the original DNS field. And then there's the thick black line, which is the filtered field, U filter. It's very obvious. The original line contains a lot more frequencies. There are many more variations. The thick black line is smooth, right? So it's better. So the thick black line, now because it contains only certain range of frequencies, you don't need to use very fine mesh to solve the problem. You can use coarser mesh and solve the problem. Okay? So that's where the computational advantage comes from. The left side, that's not change in delta G, like Gibbs free energy, not like that. Delta there is the filter width, and it's multiplied by G. Okay? That's the weighting function. So the weighting function is centered at a location. So I'll go, let's say, to location 2. Okay? And then I'll take signal on both sides up to some length. I'll take that signal, average it using this kernel that I have here that I plotted here. So this is multiplied by that signal at every point to get your filtered value. And of course, depending on the function you use, you get different kinds of filtering that's possible. Some are better, some are worse, but you'll see later that these are not critical steps in this. So we have to learn filtered variable. The filtered variable is the thick black line that has less frequency, so it's easy to solve. So you use U with a bar on top. So it's U filtered if it's like this. Now, many times, you have density that changes, especially if you do turbulent combustion. Yeah? So much of the theory for LES comes from incompressible constant density flows. So you'll see things like this. But if you want to do turbulent combustion, you cannot use these nomenclature. You have to use U tilde, with a tilde sign on top. And that's called Favre filtered variables. Now, the differences are not critical for what we are going to discuss, but you have to be aware of this. So when you see a tilde on top, you'll see this later in these slides. It's different from if you see a bar. So the bar is for incompressible constant density flows, and tilde is for variable density flows. Now, these are all details, not super critical. So I see that some of the slides didn't make the transition. It is all screwed up. So I need to fix these. But you can also look at it in spectral space. I do not want to, this is a can of worms. I do not want to start now. But you can look at this in spectral space also, which means that you change it to wave number and you look at how these functions look like, the weighting functions look like. And there are implications for this. I'll come back to this when we discuss that, but not now. So this again shows what happens if I do the filtering. So on the right-hand side here is the energy spectrum. So I filtered the signal, and once I filter the signal, I can now plot its energy spectrum compared to the original energy spectrum. Now, what I started with was by saying, I'll put this vertical line, the red line, and then everything below that is going to go off. But what I quickly find is that that scheme that I have will not work in practice. To do that, my G has to be what is called a spectral filter. And if it's a spectral filter, it will not work in any spatial simulation when we do partial differential equation. You can only use a spectral method to solve it, which only works if it's a periodic box, which none of the gas turbine combustors are, right? So if you have an inflow and an outflow and it's a complex geometry, you cannot do the spectral filtering. You have to do what is called a box filtering. And when you do box filtering, that sharp line that I drew no longer exists. Okay. Did you have a question?
No,
Oh, okay. Okay, all right. Okay. It looks more like this. So now the original spectrum is that line that's there. The dashed line is what I get when I use my box filter. The box filter is the example that I gave you. I take a small box of size some filter width, I average everything inside, and I make it into one velocity. I call it U bar, which intuitively makes a lot of sense to me. I can easily understand what LES is. But if I do this, it no longer satisfies my original hypothesis that I can cut off very crisply all the small scales. Instead, I get this messy structure now. I applied that filter, and what happens is I retain some of the scales below that cutoff, but most of it is gone, but it's not a clean removal. So there's still some small scales left. And it turns out that's every idea in itself contains the seed of its own destruction, and this is what it is. So once you have this filter, the Gaussian filter, or this box filter, it slowly takes you away from your ideal world of a sharp spectral cutoff. So now you have left with some more small scales, and you don't know what to do with them because you're proceeding with modeling, assuming all the small scales are gone. I'm going to just replace them with my model, but then there are these things left over. So what do you do with them, right? And that's the problem. Okay, this is the inherent problem. So whenever we say we do LES, people will always show you that spectrum and put that vertical line. So this is the common way. Like, I'm sure many of you are going to do this in your PhD defense, right? This is routine. But then what you won't say, because by the time you'll be an expert on LES, so you don't want to bore your committee with all the details, you will not talk about the rest of it. But what happens is you write it, and then there's a bait and switch, right? So you say, I'm going to do the sharp spectral, but no, I cannot do this for anything practical, so I'm going to use this box filter, and so I have this stuff that I don't know what to do with, okay? And that's a big problem. So this becomes a bigger issue when you have combustion on top of this. But we will proceed as if that doesn't exist, because that's what we do in LES. We always ignore all these problems, and we just keep pushing, right? So this is when the density actually changes. So you have now a variable density flow. So now you need rho, the density, and you filter the density, you get rho bar. Rho alone does not have a tilde on top, it's always with a bar. U, again, now it's density weighted filtering, so it has a U tilde on top of. Okay? So when we write equations for compressible or variable density flows, you'll always see this U tilde appearing in equations. This slide confuses more students than I can count. Okay? So this is what happens. I spent the last 15 minutes telling you there's a spectrum, there's a sharp spectral cutoff. I apply some mathematical procedures, which we said we won't discuss today because it's the end of the day. Then I said, oh, I cannot use it. I'm going to use box filter. Okay. So I said, okay, fine. And then I do all of this. And I said, I'm going to filter the equations because I do not have the original field anyway. So I'm going to solve only the filtered equations. So I take continuity equation. I apply all of these rules. And then I get this equation, which if I remove the tilde and that bar on the row looks identical to the continuity equation. Right? Nothing has changed. G, which I said is a very important thing, it's the filtering kernel. There's a filter width, all these things. It's all gone. The filter width is nowhere to be found in this equation. It's only if I give you this equation, you will not know what I use as a filter width to get that equation. Right? It's not there. So I have made special assumptions on G to get rid of it. But by getting rid of it, I have an LES equation that, for all practical purposes, has no true meaning. It's just another equation that looks like the original equation. And, if you didn't know anything about CFD and I gave you that equation, you would solve it using some coarse mesh anyways, because you're not going to solve using the finest mesh. And if you did that, you're already doing LES because you're not using the finest mesh. And you're solving the same equations. So this is very important. This is the most confusing part about LES. You go through all these steps in theory, and you derive all these equations, and in the end, you get the exact same equation that you started with. Okay? Only for continuity. It doesn't hold for the other one. But it's important to remember this. The G factor, the factor that you do for the convolution, goes away. It's gone. So the notion of what is filtered with is not there in the filtered governing equations. So you have to instrument delta into these equations some other way, right? And the only other thing we have now left is the modeling. So somehow all of these things that I'm accumulating, all this garbage that I'm accumulating, all has to go into the model. Okay? If I don't do it properly, then the model also will just generate all kinds of random stuff. So I made the original idea for doing this is to get away from what's called RANS, Reynolds Average Navier-Stokes equations. And I don't know if you guys have used RANS at all. This is horrendous. So you solve equations, very simple to solve. You can just use your laptop. If you have access to Fluent, which every university seems to have access to, you can solve like very complex things using RANS. And RANS will give you whatever you want it to give you. Because there are coefficients in RANS that you can tune whichever way you want, and you'll get any result. Like flow will be turbulent, laminar, it will transition, flames will burn, extinguish, everything in one simulation. That was the problem. And the promise of LES is that you do not have to go through that extensive modeling. Somehow, because you're only modeling the small scales, and somehow they're not important, which we said is also not true for combustion. But let's say it's not important, it's better. But this equation does not give you that. It tells you nothing new than what you had originally, except that now you have the ability to solve it in a coarse way. That's about it.
Question. Okay, fine. You've transformed the equation, but don't you need to transform the boundary conditions too?
Yeah, you can transform the boundary conditions too, and they will also not contain these terms. That's the problem. So you will look like something that has different variable sets involved, and because I'm using rho bar and u tilde, I'm implying something from that, right? I'm not saying there's not a difference, but what am I implying? I don't have it in the equation. That's the main problem. So ideally, I want to have G and delta as part of this equation, so I know how I got to these without having to tell someone what I did. Now, this is not the case if you go to other equations, like continuity equation is some, because of the nature of it, it has that unique property. But if I go to the momentum equation, okay, and I can do the same filtering procedure for the momentum equation, and what I'll get are these equations, the third set of equations that I have, and you see that I have this ui tilde. So momentum, it's three-dimensional. All turbulence is three-dimensional. No LES should be two-dimensional. So whatever else you learned from this course, do not do two-dimensional LES calculations. So LES is three-dimensional. And ui tilde is the equation for the ith component of velocity. The three components, we live in a three-dimensional space. The three components, so it's u1, u2, and u3, right? And what you see in the second term is uj, ui with a giant tilde on top of it, okay? So what I mean is I take two fields, ui and uj, multiply them, and then filter what I have, which it turns out, if you know a little bit of signal processing, is different from first filtering uj, first filtering ui, and then multiplying them. So the product of the filtered quantities is not the same as the filtered product. So that is what is called the LES closure problem. So the last statement tells you that. So uj, ui, if you multiply and then take tilde, it's not the same as first filtering and then get. Now the reason why this is important, you're doing ui, you're solving an equation for ui tilde, which is the filtered velocity. And to solve that filtered velocity, you need to know what this correlation is, uj, ui filtered, okay? And you cannot just ignore it. If you do that, you'll get nothing. Like you can solve equations, it will not work out. So you do need to reconcile this difference. If uj, ui tilde is not available to you, how are you going to model it? How are you going to represent that correlation? And that becomes the LES modeling problem. And for combustion modeling, it will be similar. We'll see that next. But this is for the turbulence modeling problem. And what Smagorinsky figured out was that you can model this correlation by using a very simple formula based on what's called Bushnell's hypothesis, which has been there for, I think, from the 1800s, if not, or something very, very early on. And if you do this, you can come up with a closure that you can apply here. So that's the main discovery. Right? So you can do that. So anyways, this is your closure that you have to model. Okay, and this only says in statement what I just told you. Like there's a discrepancy between what we think of as a filter width and what is being used there. So we have to remember this discrepancy here. So I won't belabor this point, but I'll go to the next one. So if I were to take these equations, okay, and now I want to filter them, together I will write these equations to look like this, okay? And what I've done here is just a rearrangement of terms. I've not removed anything. So you see that there's ui, uj filter, which I need to model. So what I've done is I've added ui tilde, uj tilde, which I know already, subtracted the same term from there. So on the whole, it's the same. But now I've introduced this new term, Tij, to be this quantity right here, okay? And whatever I want to do, I say I want to model that quantity. So these are called the subfilter stresses. So if you do RANs, Reynolds stresses or U prime, V prime, average, things like that, it's very similar to that, but it's in LES and it's at the subfilter level. So these are called subfilter stresses. So I need to have a model for this term here. So that's the main thing. Now everything else there is fully resolved. You don't need to model anything. It's only this term that needs to be modeled. So if I can model it, then I can get around this idea of having to resolve all the scales. So you should have an appreciation for how this actually looks. So if I did DNS, this is on the left, And these are actually, they're all roughly the same. The two images on the left are for two different inflow conditions. So one is a square inflow of a jet, the other is a round inflow, something like this. So they're not that different. And then the flow comes out, and you see that there are some structural differences. The guy at the top looks like it's more laminar. The one at the bottom has more resolved structures, things like this. Before LES existed RANS. It exists now also. It's not like it went away. It's there. But RANS was the first method to be introduced. And when you do RANS, what you will do is you will do what's called Reynolds averaging. You'll time average, let's say, for this problem. More formally, you will do ensemble averaging. But you will time average, and it's no different than taking this DNS, having a long exposure photograph, and trying to model that long exposure photograph. So that's what RANS is. And so if you write the equations for RANS, it will just look like a laminar flow at a much higher viscosity, low Reynolds number compared to the original flow. That's what those equations will look like. So if I solve RANS, it will look like the right-hand side. So that's what you get from RANS. But if you go to LES, it's a little different. And you get these pictures. So on the left is DNS. That, I think, is from Sandia, from Jackie Chen. And then on the middle is the LES calculations of the exact same geometry. And what you see, this is a flame. This is a lifted flame. So the flame is not attached to the bottom. There is fuel coming in through the middle, heated air to the sides. And so the turbulence mixes them, and then the flame will stabilize at some point. And you have to capture the flame stabilization. And so this is from my own group. I think it's 10 years ago or something like this now. And if you look at the LES, it's done on a much coarser grid. I think the LES is about like 1,000 times or 10,000 times faster than the DNS, okay, because it's a coarser mesh. And what you see is that the LES captures that flame height, which is where the purple high temperature region is, roughly the same, but it looks more laminar. It doesn't have as many structures as the LES. And so that's the difference that you'll get from this. So on the right-hand side are also simulations. And I think these are the last simulations I did by myself. And since then, I've had PhD students. At this point, I don't even know how simulations are done. I just talk about them. Yeah. So these are simulations. And at that time, so this is 20 years old. Yeah, this is vintage calculations at this point. And these simulations, we had to show it to a company called SGI, and they would tell us how to visualize them or something like this. And so we got frustrated with them, and we wrote our own 3D visualization. And that's what this is. So it's light being emitted by the flame, and then you track it, and then this is how it looks. I think it's a movie also, similar to others. I do not know if it works. Oh, it works. Okay. And that's for a different flame where there's a bluff body in the center, and then you have this flame that's forming. And this is very peculiar because what happens in this particular flame is that the flame often quenches and comes back up. So if you take an average, it will look like the flame is present half the time, not present half the time. So temperature of 2500 Kelvin and 300 Kelvin, the average is 1400 Kelvin, right? So the experiments will show 1400 Kelvin temperature average. If you do Reynolds average Navier-Stokes equations, you cannot get it. You'll either get the extinguished state or the burning state, but not the intermediate, which is not physically possible. So LES could capture this. So this was a big revelation at that time. It was like a earth-shattering calculation. I just said myself, but it's an earth-shattering calculation. And so we could do these complex flows, right? And the thing that we realized from this is that what LES is good at capturing are these kinds of problems where you set a boundary condition. It doesn't matter what models you use. We'll talk about the models tomorrow. You use some set of models. The combustor needs to have some physics that's changing with time without you adjusting the boundary conditions, okay? Which it turns out aircraft combustors and stationary gas turbines do quite often. So they can change operating, the flame shapes can change. Flames can sit higher up or lower down for the same operating conditions sometimes. They can move back and forth. So those kinds of problems where nominally the boundary conditions are stationary in time, but the flow features are unsteady or they're exhibiting limit cycle behavior or different steady points, attractor points. For those kinds of problems, LES is very useful. So that's the instantaneous picture. If I take it, time average it, and run Lagrangian particles, I would get these streamlines. And if you did experiments and you take PIV and do the same, you'll get exactly the same picture. But they're coming from a highly unsteady flow where the structure is changing all the time. Yeah, so there's a difference between the two. Okay, so I'm nearly at the end of this. So I'm at slide 69 of 70, and then I just moved to slide 70 of 70. So we're done with all of this. But I wanted to understand a few key aspects today, right? So we started by saying turbulence has scales, and the scales lead to small lengths, the smallest being eta, which we cannot simulate using modern computers. So we are going to use LES, and for LES we need to do filtering, and if you do filtering, you have to do modeling. Yeah. But the promise of LES is that even though combustion happens at the small scales, we are somehow able to overcome that limitation. And as a result, we are able to do things much faster, right? So you're able to simulate the whole geometry. I have this thing in the middle. Tomorrow we'll talk about this more on what are the limitations of LES. That's very critical. We started looking at it a little bit. So if you have the same boundary conditions and over time, if features inside change, then LES is good. But what is not good is that if you change the boundary conditions, the time it takes to adapt to the change, those features you cannot capture correctly. So for that, a little bit nuance in how we think about this problem is needed. Yeah? So this is all I had for today. Okay? So we have like 15 minutes left. If you have any questions, I can answer those questions. I'll be here. I can talk to you about this, however you want to do it. So let's first take a few minutes. If you have any questions that you want to ask me right now.